Welcome to The Explainer. Today, we're diving into one of the biggest challenges facing our future energy grid. And, believe it or not, the surprisingly local solution that could have a massive global impact. Okay, let's jump right into this paradox. We're all pushing to add more renewables, solar, wind, to the grid, which is great. But here's the twist. This flood of new green energy is actually creating a huge new problem, one that could make our power grid less stable and a whole lot harder to control. To really wrap our heads around why this is happening, we first need to look at just how fundamentally our electric grid is being rebuilt from the ground up. You see, for about a century, the grid was pretty straightforward. You had a few huge power plants pushing out a steady, predictable flow of electricity. Simple. But the new grid, it's pretty much the exact opposite. It's this sprawling, distributed network with countless power sources, everything from solar panels on your neighbor's roof to giant wind farms. And their energy output? It goes up and down with the weather. It's totally unpredictable. These thousands of new sources are called distributed generations, or DGs for short. And if you imagine the power grid as this perfectly synchronized orchestra, well, we've just invited thousands of new musicians to come on stage, all playing their own tune whenever the sun shines or the wind blows. This creates a massive challenge. How do you keep the whole orchestra in harmony? Or in grid terms, how do you keep the voltage stable? Because if that voltage isn't managed perfectly, and I mean perfectly, it can lead to all sorts of problems, from flickering lights in your house to, well, catastrophic widespread blackouts. So this brings us to the million-dollar question. How on earth do you coordinate all of these new, unpredictable musicians to play together and keep the power flowing smoothly? Well, the first big idea was, let's hire an AI conductor. Researchers turned to a specific kind of artificial intelligence that's designed to teach a whole team of independent agents how to work together. The method is called multi-agent reinforcement learning, or MARL. And the specific approach they tried, which is known as the CTDE framework, seemed like a brilliant idea at first. So with this model, you have essential AI, our conductor, that tries to listen to every single DG, every single musician in our huge orchestra, all at the same time. It hears what they're all doing and then gives them feedback to guide their actions, trying to keep the whole system in tune. And it worked, but only for, let's say, a small chamber orchestra. Because as the grid and our orchestra got bigger and way more complex, this whole listen to everyone at once strategy, it ran into a massive, unavoidable wall. The original research paper is really blunt about it. It says the framework just couldn't scale because of something they call the notorious curse of dimensionality. So what is this curse? It's basically just a fancy way of saying information overload. Our poor AI conductor was getting totally overwhelmed trying to process what thousands of musicians were doing all at once. The more DGs you add, the problem gets exponentially harder until the AI just gives up. It can't keep up. Because of this fundamental limit, all the previous research using this centralized AI model hit a really hard ceiling. They could only manage to successfully control about this many agents. 40. That's it. 40 is absolutely nowhere near the thousands or even millions of DGs that a real-world smart grid is going to need to handle. The AI conductor was a cool idea that, in the end, just couldn't scale. The solution wasn't working. So the researchers went back to the drawing board, and their new idea was so simple but so brilliant. Instead of trying to give the conductor super hearing, they completely changed how the musicians communicate with each other. So instead of one central conductor trying to listen to everyone in the whole orchestra, what if each AI agent, each musician, only had to listen to the musicians sitting right next to them? That's the simple but incredibly powerful idea behind this new Scalable Network-Aware Framework, or SNA. And the reason this works so well is because of a scientific principle called the exponential decay property. The paper proves something that feels really intuitive, right? A voltage disturbance at one spot in the grid has a huge impact on its immediate neighbors, but that impact fades out exponentially the farther away you get. It's just like a ripple in a pond. So the SNA framework just leans into this. By having each AI agent only pay attention to what's happening with its direct neighbors, it radically cuts down the amount of information any one agent has to deal with. It completely sidesteps that curse of dimensionality, and that allows the entire system to scale up beautifully. Okay, the theory sounds fantastic, but does it actually hold up in practice? Let's get to the results and see how this new listen to your neighbors approach did in a big simulated test. The researchers built this complex test grid, and they used the SNA framework to control this many individual agents, or DGs. 114. That's nearly 3 times the old limit of 40. This is a huge leap forward. It proves that this new framework can absolutely handle the kind of complexity we'd see in a real modern power grid. And this table just makes the difference so clear. The old CCDE framework, poor scalability, and its performance tanks in large grids. The new SNA framework, excellent scalability and superior performance. It's a total game changer. And you can see the real-world benefit right here. This chart shows the average voltage fluctuation. Old school controls, lots of fluctuations. The old AI framework is better, sure, but the new SNA framework is the hands-down winner, keeping those voltage swings significantly lower. And what that means is a more stable, more reliable grid for all of us. So, what does a breakthrough like this really mean for the future of our energy system, for our planet? When you boil it all down, the SNA framework gives us a practical, scalable blueprint for a truly smart grid. It can handle a massive number of renewables. It slashes communication costs because agents only need to talk to their neighbors. And it's flexible enough to work with all sorts of different AI algorithms. This is basically a roadmap for the self-regulating grid of the future. And it leaves us with this really fascinating final thought. For a problem as huge and global as reinventing our entire energy grid, the most powerful solution wasn't some bigger, more powerful central brain. It was empowering countless smaller parts to cooperate intelligently on a local level. It really makes you wonder, doesn't it? What other global challenges could we solve by thinking just a little bit more locally?